Okay, so good afternoon, everybody. Welcome to the 5th IQOQI Colloquium. So today it's a pleasure to have Professor Reichel, Jakob Reichel, as a speaker. So let me introduce his vita. So he studied physics at the universities of Bonn and Munich, and he finished in 1991. Then he moved to Paris to do a PhD in the group of Cohen Tanucci at his laboratory in the Casse Lab-Rossel de l'École Normale Supérieure. And he did his thesis under the supervision of Christoph Salomon. Then he went back to Munich, actually for a period of 7 years, first as an assistant and as a Privatdozent in the physics department of the University of Munich and the Max Planck Institute for Quantum Optics. And this was in the division led by Professor Hensch. And he got his habilitation in 2003. Then in 2004, he went back to Paris as a professor at the Université Pierre et Marie Curie, and which is also a member of the Laboratoire Casse Lab-Rossel, sorry for the pronunciation, and where he's leading a group on atomic microcircuits. So his research, so he's very well known for his research on atom chips, on trapping cold atoms in microcircuits, as well as to couple them to cavities, in particular to fiber-based cavities. So in particular, he and his colleagues were the first to trap atoms in an atom chip and to make a Bose-Einstein condensate there. He also showed strong coupling of these cold gases to a cavity. And more recently, he has been interested in multipartite entanglement, how to generate it using quantum xenodynamics and so on. So he has received many prizes during his career. Many of those were for young researchers, and later on he also became a chair of excellence of the French Ministry of Research, a senior member of the Institut Université de France, and recently in 2015 he got an ERC advanced grant. So he also says that most of his inspiration comes from playing chamber music, in particular violin and viola. So we hope we will see a lot of the results of this inspiration in this talk. So let's please welcome the speaker today.
Well, thank you for this kind introduction, and I mean it's an immense pleasure to be here and share with you some of the work that we've been doing over the year. And I mean, these are just exciting times for quantum physicists, as you all know. I mean, what used to be thought experiments has become experiments that we can do in the lab. We have this fantastic control over quantum systems, although it's never good enough. But still, it allows us to do in the lab what used to be these thought experiments, and in doing so, we get new ideas, and we now start to do things that the founding fathers of quantum mechanics didn't even dare to think about, which is an interesting phenomenon in itself, right? This interplay between theory and experiment that we witness there. And so as we do so, we get the impression that, well, this is now so radically different from everything that you can that you're experienced with in the classical world. There must be something to be done with that, and of course what is now being called the second quantum revolution, with its quantum technologies and pillars and all that, is just a first manifestation of that. And even though I personally think that the most interesting quantum technologies are still to come, those that we have identified already give us a lot of matter to think about, and to try to realize in our experiments. And one thing that you realize when you look at all these different quantum technologies is that multiparticle entanglement, so the kind of entanglement that goes beyond simple Bell states. Well, the Bell states we think we understand quite well by now. multi-particle entanglement, maybe a bit less. We have this huge Hilbert space. We maybe don't fully appreciate yet what is going on there. We can't even measure entanglement correctly. So definitely a lot of the interesting stuff is hidden there. And that is something that all these quantum technologies have in common, whether it's quantum computing, where essentially you build a gigantic entangled state to extract some information from it, or quantum simulations, quantum metrology, and so on. So if you want to realize these things in the lab, you have a few options, and all of them excel in different aspects. So far, none of them gives us everything we want in a single package, but nevertheless, with what we have already, there are a lot of exciting things to be done. And I mean, just to cite a few, there are superconducting circuits where you can realize qubits by exploiting the power of microelectronics that we already have in order to realize quantum systems. But when we do so, maybe we can turn down the microphone a little bit so that we don't get that feedback. But the problem with these qubits is that they are not all alike, and so when we couple them, we need to tune them into resonance. But the tuning devices introduce heating, and so for the time being, they are coping with essentially random coupling when the system gets large, and there's this idea of quantum supremacy, which essentially is the idea of you calculate garbage, but garbage which is hard to simulate, and then you try to show that indeed you've done something that would be hard to do on a classical computer, even though you can't control what you're doing. On the opposite side, you have ion traps, which are like the gold standard of what you can do today with really identical qubits. Identical because nature gives us identical atoms, and that is makes these qubits of such a high quality. But the really mind-boggling thing is what the degree of control over these qubits that is achieved in the system. And so this quest of being able to really do arbitrary operations on n qubits is, I think, today best embodied in ion trap experiments. And so what about cold neutral atoms? What is left for them? Well, certainly today they can't compete with this control that ion traps offer. Really, the one thing that I see in ultra-cold atoms is that seen as qubits, these are cheap qubits. You can get huge numbers, and in terms of being identical, well, they are also very good by the virtues of nature herself. And so essentially, what is being done with neutral atoms is you give up this ideal of being able to do any arbitrary operation, and instead you settle for some form of interaction that you deem interesting, and then essentially you need to build an experiment for a single Hamiltonian or class of Hamiltonians. But that you can do in such a way that you can scale up the number of qubits to fairly high numbers, and so that makes this the setting that excels in particular for quantum metrology. Things like clocks and interferometers, where you gain in signal to noise with the square root of the number of qubit atoms, and then it is known that this can be further improved by using entangled states. And of course, in quantum simulations, you also have a similar approach to the scaling. And so all these systems have their virtues, and but in order to create the entanglement, what they all need, of course, is some form of interaction to create the entanglement. And there again, there are lots of different types of interactions that you can have, and I won't bore you with a list here. And let me just tell you the one that I'm going to talk about today, which is using an optical cavity and using one particular optical mode in that cavity in order to create entanglement. So that is what I'm going to talk about. But even that is not enough to focus down on just one class of experiments, because what you can do with such a mode in the cavity is fairly versatile and can lead to really different forms. Actually, this sound is really a bit annoying. Couldn't somebody turn down the volume a little bit? Or maybe I can do it here. What about this? Yeah, that's better. Oh, you can stay here. Sorry. So, yeah, that's now I feel better. Depending on how you set up your cavity and how you tune your parameters, you can set it up in such a way that you get mechanical effects. So the coupling between the optical mode and the qubit atoms in the cavity takes the form of some form of coherent recoil that leads to a momentum distribution that has interesting features, and then you can get self-organization and even quantum phase transitions. You can also couple several fields at once and use the atoms to redistribute photons in a coherent way between these modes. These are all this gives rise to interesting whole classes of experiments that you can do. There's also much more elementary things conceptually, which is nevertheless extremely important for quantum technologies, which is quantum memories and switches for quantum networks, where you just exploit the fact that the field of the cavity allows you to couple extremely well to a single emitter or an ensemble of emitters, so that you can exchange the quantum information between flying qubits and stationary qubits. And finally, you can exploit the fact that if you have an atom or an ensemble of atoms sitting in that cavity, and the coupling between the cavity field being a quantum entity and the qubits another one is strong enough, then if you just shine light onto the cavity, which you can do either by a transmission or reflection measurement, or with a transverse beam, then you cannot no longer consider this coupling as just one field that has a given amplitude and phase, and then calculate its effect on the atoms. But you have to take into account the back action of the atoms onto this field, and you get a coupled state, and this is what makes the system interesting. And with this approach, you can produce many-body entanglement of different forms, and in particular, you may have heard of experiments with which produce spin-squeezed states in that way. And I'll tell you about this and actually a more general way of using this coupling in order to produce entanglement. In order to do so, I mean, we have to kind of start at the beginning and just spend one slide looking at the basic ingredients. So here we have this cavity with its standing wave field, and here for the time being we put in a single two-level atom here, and suppose that the cavity is tuned close to resonance with the atomic transition, and now you scan a probe beam across the resonance, and if you just had the empty cavity, then you would see here this Lorentzian transmission shape. But as you put in the atom, if the coupling quantified here by this quantity that I'll come back to is big enough, then instead you observe a split resonance, which is called, for historical reasons, the vacuum-Rabi splitting, which is really actually a weird name. It would be better named, if at all, you could name it the single photon Rabian splitting, because its splitting corresponds to the Rabi frequency of the atom in the field of a single photon in the cavity mode. And but actually, you can also explain this phenomenon in a completely classical way. Once you know the dispersion relation of your atom, it's just actually, as long as the atomic excitation remains weak, it's the same phenomenon of coupling of two pendula or coupling of two oscillators that you also get classically. And the coupling constant actually is called G here, is this single photon Rabi frequency. And in order to observe something that is coherent and thus interesting, you need this coherent coupling constant to overwhelm the two incoherent time constants of frequencies that you have here in the system, which are kappa, the loss rate of your cavity, and gamma, the excited state decay rate of the atom. So you can define this quantity called the cooperativity here, which compares the coherent coupling rate to the geometric mean of the two incoherent rates. And it turns out that more or less all phenomena in such a setting can be described in terms of this cooperativity constant here, and you essentially never need these constants here individually. And the interesting things happen when this cooperativity is larger than 1, so that the coherent coupling dominates. So that puts a premium on cavities that maximize this ratio, and therefore it's interesting to look at how this cooperativity scales with the cavity parameters. So the cavity parameters are essentially the cavity finesse, which quantifies how good the mirrors are, so how many bounces the photon can make before it either leaks out or gets absorbed. So that we have here in the numerator, and then the cross section of the beam is here in the denominator, and so you see that a good cavity for these purposes here has a high finesse, not so surprising, and has a very small mode waste. So the fundamental experiments in that field with optical cavities were done in the late 1980s, early 1990s, well, throughout the 1990s actually, by a few groups, but we need to cite here the work of Jeff Kimball, who was really the motor in pushing that forward. And these experiments are in many ways the dual of the experiments done in the microwave domain by especially by Serge Haroche and this group, with the role of the cavity of the photons and the atoms actually being reversed between the two fields. The hallmark of entering the interesting regime is when you observe this so-called vacuum Rabi splitting, as in this experiment here from Jeff Kimball's group from 1992. And now, once you are there, what happens if you replace this two-level atom? Well, you can always extend it to being a qubit by adding another stable state, which is not coupled to the cavity. That's always possible. The physics essentially remains as before. If the atom is in this state, it's as if it wasn't there. And so you see right away how you can use such a cavity as a qubit detector. If the atom is in the 0 state, then the cavity transmits a resonant probe beam. If it's in the 1 state, then you get this vacuum Rabi splitting, and the probe beam actually is reflected. Right. From now on, we will deal with these qubit atoms, and now we will add more of them. What happens then? Well, if you do that, as long as you don't excite the system too strongly, so that you always have less than one photon at a time, then actually what happens is very simple. The atoms being collectively coupled to the same mode collectively absorb and re-emit light. And because they do that, actually this coherent coupling constant now is multiplied by the square root of the atom number. And apart from that, everything remains as before. So you have this whole ensemble of atoms interacting with the mode like a big super atom. And when you look at the level diagram of the coupled system, this is what you get here. So here we have on the x-axis we have the detuning between the cavity and the atom. So on a resonant cavity would be here, and on the y-axis we have the energy of the coupled states, which would be the energies at which an incident probe beam would be resonant with the coupled system. And you see that for a single atom you get these two thick lines here. The gray line is the empty cavity. Scanning like this, you get the vacuum Rabi splitting, and you see that as you increase the number of atoms, the distance between the two peaks will simply increase. And so in that way, what we see, and this is an important fact that you need for in the following, is that the eigenstates of the coupled system are the so-called Dicker states that you can represent on an n-atom, n-qubit Bloch sphere, like these circles here parallel to the equator. That are the eigenstates of the systems and of the system, and these are the states that you will detect when you send a probe beam onto the system. And by changing the cavity detuning, you can tune into resonance with any one of them. And each of these Dicker states corresponds to a well-defined number of atoms in the coupled state. Okay? So that will be the phenomenon that we start from, and that we will exploit now in the experiments. And actually, realizing that this is possible is already good news, because because the coupling is symmetrical and couples all these atoms in the same way. That is why we are dealing with a symmetric subspace, with a subspace of states where all the atoms play a symmetric role. That's not so surprising, and that's what limits us to the surface of this Bloch sphere. But why do I say that it is good news? Well, this is because many of our preferred entangled states, like cat states, W states, spin squeeze states, they all live in this subspace, and so we get the feeling that it may be possible to use the cavity to generate them. But before we can go there, of course, we need the cavity that can do all that. And as I already told you, that means that the mode waste should be as small as possible. And the scale to compare to here is the atomic scattering cross section. Now that's pretty small, right? That's essentially lambda squared. And so you would like to have a cavity that focuses down its mode to a lambda squared. And for a long time, that wasn't really possible. There were approaches for doing it by microfabrication, and that works for solid-state systems, but not so well for atoms. The cavities that the early cavity QED experiments were using actually had much larger wastes. So in terms of micrometers, it's often as big as 20 microns, where the wavelength is submicron, and then you have to square that. So for the cooperativity, that's bad news. And so what you want to do is to somehow miniaturize your cavity mode. And that was a quest that started in the early 2000s. Here's a gallery of cavities that have been pursued essentially for this reason. And there would be a lot to say for each of these approaches. There are these photonic crystal cavities here, for example, that are very interesting. But most of these alternative miniaturized cavity types couple to an emitter through an evanescent wave, and that's not so easy to combine with ultra-cold atoms, because it means that you will be close to a surface, and then you get decoherence effects due to that surface. The good old Fabry-Perot cavity doesn't have that problem, but it did have this problem of having a mode that is more than 10 times larger than what you would like to have. And so at the time, when we started developing our own cavity, the idea was, well, wouldn't it be nice if we could realize just a good old concave mirror, but with much higher curvature than in macroscopic cavity. And while we are doing that, why not do it on the tip of an optical fiber so that it will be automatically fiber coupled? And then if you could do that, well, then you could have several cavity configurations, like putting two of them face to face, building a microfabi pro, or putting one of them facing a flat surface so that you could actually scan a cavity across a surface, which in the meantime has been realized as well, although I have no time to talk about it. But the first thing, of course, was to learn how to make a good, very small, strongly curved mirror on the fiber, so that the cavity mode would shrink and that the waist size would get closer to the atomic scattering disk diameter. And indeed, we succeeded in doing that by using a laser machining technique. Here's a micrograph of one of our earlier attempts. So what you have here is an optical fiber. The diameter is 125 microns here. And what you faintly see here in the middle is a little depression with the radius of curvature of about 100 microns, which is to be compared to the smallest radii that could be done by traditional superpolishing techniques, which is on the order of 10 centimeters. And that's the factor that we gain here. But of course, it was necessary to do that with extremely good surface quality, because otherwise our photons would get scattered and the cavity finesse would be too low. And miraculously, it turns out that when we do this machining with a CO2 laser, then you can get that. You can get this very small radius of curvature plus a very good surface quality, because you get a combination of laser ablation, you evaporate material, and local melting in a very thin layer close to the surface, which is responsible for smoothing the surface and giving you a surface quality that is actually breathtakingly good. Here are a few numbers. So you can make cavity mirrors that have a surface quality that is close to the best, not quite as good, but very close to the best you can do with the best known alternative techniques, enabling you to get a cavity with a finesse of several hundred thousands. The best have been done here in Innsbruck, by the way, in collaboration with our group. And radii of curvature down to below 10 microns, which allows you to make a mode waist smaller than 1.5 micrometers, more than a factor of 10 smaller than with other techniques, and enabling you, taking it all together, to realize a cooperativity larger than 100, where with the traditional techniques you are stuck around a value which is almost 10 times smaller. So that is the technology underlying the possibility to do the high quality cavity QED experiments that I would like now to talk about. But this technique is actually evolving continuously. And before I move on, just to kind of whet your appetite, I'm showing you a result that there's somebody here in the room who is familiar with. It's the whereas in the early days we just shot at the cavity at the mirror just once to define our mirror. Now we have a dot milling technique close to laser dot printing, which where you shoot at the same fiber up to several hundred times in order to define the shape that you want. And I could go on talking about that, but just to give you an idea, I mean, it's work in progress. These cavities are still improving a lot, and the experiments that I'm going to show just use single mirrors. But by now we can also make more complicated shapes like this one here, all on the scale of 100 microns. And the cavities that are being used in the experiments that I'll show you now. Actually, the first generation of these fiber cavities, so are limited in finesse to values that by now we can do much better. So what I'd like to show you now are experiments where we put an ensemble of atoms into such a cavity in such a way that all the atoms are identically coupled to the mode. Now, if you put the atoms into the cavity mode at just any place, then each atom would get a different coupling to the mode. That's not so good. You would like to have them all with all identical couplings. And our way to do that was to first produce a Bose-Einstein condensate, not so much because of its quantum features, but just because of its small size, so that we could then fit the whole condensate into a single antinode of the cavity mode to get this identical coupling. In order to do that, we used the proven technology of atom chips that I have no time to elaborate on further. There's a book about it if you care. Essentially the idea is you have microfabricated wires that you run current through to define magnetic potentials that are extremely well controlled and can be very strongly confining, and allow you to position your atoms very precisely. So the combined thing looks like this. Here you have this atom chip. You move the atoms to this place here, and this white thing here is the holder for the cavity, and the cavity itself is so small that you can't really see it here. But in principle, it's just two of these laser machine fiber mirrors face to face, and the whole thing has a cooperativity of 180 for the cycling transition. And the absolute numbers are given here. And what we put into it is an ensemble of rubidium atoms, up to a few thousand of them, that we can coherently transfer between two qubit states shown here, using radio frequencies, actually microwaves. So we can do Rabi oscillations as we like between these two states. And then this red state here is coupled to the cavity mode. That's our basic situation. So we have these two ways of interacting with the atoms, either this coherent radiation here, or the cavity mode. Now, all the experiments that follow will proceed like this. So first we produce our BC, we position it inside the cavity mode, and then we further confine it in an optical lattice, of which we populate only a single site. And this site is chosen such that it is perfectly overlapping with the resonant cavity mode, which is the one that I've been talking about all the time before, and which will produce the coherent interaction. Once you can do that, so here you see a first experiment, and Yves Colomb, who is here, has recorded a long time ago, which is an experimental realization of the coupled level scheme that I've shown as a theoretical plot before. So that shows us that we are where we want to go. And now what do we do? Well, actually, there's a whole class of experiments that you can do by just exploiting the cavity in a very simple way, which is to use it as a detector for the state shown here, where all your atoms are in the zero state. And actually all I'll be doing in the next 5 or 10 minutes will use the cavity in that way. How does it do so? Well, just by exploiting what I've explained before. So if all the atoms are in this state, then they are not coupled to first approximation, not coupled to the cavity mode. So if the cavity is resonant with this transition, and you have a probe beam that is resonant with this atomic resonance frequency, then this probe beam is transmitted. However, if only a single atom is in this one state here, then by virtue of the vacuum Rabi splitting, now the coupled system is no longer resonant and the probe beam is reflected. And why is that? I mean, so after all, I'm just detecting the presence of a single atom in that state here. And now you may say, oh, okay, but there are lots of ways of doing that. This you can detect that in fluorescence. That is what's being done all the time in quantum gas microscopes, for example. So why bother? Well, the thing is, because of the way we've set up this measurement, it is non-destructive in the sense that it actually projects you onto the state that you've measured. but without having side effects. When you think of it, all optical measurements that you do in free space, in the end, produce spontaneous emission, and this spontaneous emission is your enemy in this context here. If you want to entangle your atoms, you don't want to know which of your atoms has interacted with the probe. But if you create spontaneous emission, then in principle you can see where this photon came from, and so you localize, you single out one of the atoms, and that's what you don't want. Now, if you don't want spontaneous emission, it turns out then no free space method can do the job. That may sound surprising. I mean, of course, it's clear that for spontaneous emission detection, so fluorescence detection, there you create spontaneous emission. Okay, there's no doubt about that. But what about dispersive detection? You can detect the phase shift. Can't you suppress spontaneous emission in that way? Well, it turns out that you can't. You can't because if you detect the phase shift, then you need more photons than in the fluorescence case. And when you compute how much information you get per spontaneous emission, it turns out that in order to learn anything at all, well, you need to interact with so many photons that in the end the spontaneous emission is the same as before. So you need to generate at least one spontaneous photon if you want to get any usable signal-to-noise ratio at all, unless you use a cavity. But in all free space schemes, you have that problem. And that's why it makes sense to do that with a cavity. And the thing that happens when you do it with a cavity is that when you look again at what we've seen, well, either here you have resonant light in the cavity, but it's actually resonant with a state that is not populated, so it does no harm. Here now I have a fragile atom in this state that would be resonant, but there's no longer any light in the cavity, and that's why you don't get spontaneous emission in that case. So that's the basic mechanism. And you can get detection with high signal-to-noise ratio, and you can, as we've shown experimentally, get below this threshold shown here, which corresponds to a single scattered photon for signal-to-noise ratio that you can achieve with a free space scheme. So anything you can do in free space is in this gray region here, and we are below this region, so we have a better signal-to-noise ratio than you could get in any free space scheme. And for example, we can get a detection error of 10% with 0.2 scattered photons per atom on average. That's what we've experimentally determined, and that's what we can do in the cavity that I've shown to you. It's limited by several things. It's limited by the cavity finesse, but also by the fact that our cavity happens to have a biorefringence. Maybe I'll come back to that point in the end. But actually, with the progress of cavity technology, by now our curve would be much further down than this one here. But already with this one, you can do things that you couldn't do without a cavity, in the sense that this detection now tells you whether or not you're in this zero state, but it does so without generating spontaneous emission. So it comes very close to an ideal projective quantum measurement, which is funny enough is not so common in quantum mechanics. Actually, almost never you do a projective measurement. It's you have to work hard in order to do so, and here we have such a measurement. When you look at how ideal it is, well, it turns out that the number of scattered photons that you need for a given signal-to-noise ratio shown here, it scales as 1 over the cooperativity. Okay, so the higher the cooperativity, the closer to 0 gets your number of spontaneous photons, but it only decreases as 1 over c. But that's already something. The best you could get without a cavity is c equal to 1. And we had c close to 100. And one thing that you can do with that, I'm showing you, we have used that in several ways to create entanglement. I'll show you just one example, which I think is conceptually the most interesting one, which is called quantum Zeno dynamics. Now, what is that? You all know the quantum Zeno effect, where you freeze atomic dynamics by repeatedly measuring the atomic state and thus projecting back onto the state that you've measured. Now, what happens if you do a similar thing, but in a larger Hilbert space? In the Hilbert space, suppose that you have some coherent dynamics going on. So you create states that are superpositions of these individual states shown by the dots here. And for example, a Rabi oscillation driven coherently would create superpositions of lots of different states in your Hilbert space. But now suppose that you combine that with a measurement that can tell you whether you are in the left or right half of your Hilbert space. So it projects you onto that half of the Hilbert space, but if it's done in a non-destructive way, it doesn't destroy the coherences inside your subspaces. Now that's an interesting situation, because if you now drive the same coherent dynamics as before, and you drive your state close to this wall in the Hilbert space that you have erected with the help of your measurement, then something interesting happens. And it turns out that I'm not sure if there's a statement proving that, but typically, as you drive a system towards this measurement barrier, you generate multiparticle entanglement. And that is what we are going to exploit in the experiment. The theory for that was worked out by most notably by a researcher called Saverio Pascazio and actually Jean-Michel Raymond a bit more recently showed that you can generalize it into a general scheme that can generate a very large class of entangled states. But here we will just modestly try to produce any entanglement at all with this scheme, which had not been done in the first experiments that got interested in this dynamics, which could show some consequences of Zeno dynamics, but only in single particle systems. And so what we will use is simply what I've explained before. Here is again our n-qubit Bloch sphere. So if all atoms are in the zero state, if all spins are down, then we are at the south pole. And that is precisely the state, as you remember, that we can detect with our cavity. So our cavity will just tell us whether we are in this state or we are not. Okay, so using my cartoon Hilbert space again, I'm just singling out a single point in that Hilbert space. But if what I've been telling you was right, then the dynamics in the rest of the Hilbert space should remain coherent. And so what we will do is start at the north pole this time, all spins up, and then we will drive just a stupid old Rabi oscillation towards the south pole. But the south pole is being blocked because at the same time we switch on the probe beam and thus verify all the time that the population in that state remains zero. Now what will happen if we do that? Well, it's easy to simulate. In some sense, your state will flow around that pole instead of reaching it as it would if the measurement wasn't there. And if you simulate the thing, here's what you get. We're looking at the south pole of the sphere. And instead of remaining just a blob, you see it forms a ring. And this ring is a very good approximation of this entangled state here, which, depending on circumstances, is called a W state or first Dicke state. And it's just a state that contains exactly one excitation but distributed over all the atoms. Okay, and that is the state that we will get close to by just driving a Hilbert, by just driving a Rabi oscillation, but while we are doing this measurement. And so here is the experimental results, looking at the south pole of the Bloch sphere again, but this time recorded experimentally while we drive this dynamics. Here on the different graphs, you take your state tomography at different moments. And you see that there is a moment here close to the pi pulse time where indeed you get something that resembles a ring structure. And by the way, this here is the raw data that we are recording with the tomography method that I'll tell you more about in a minute. And here is maximum likelihood reconstructions. But already in the raw data, you see that here you have this higher probability around a point of low probability, which is this ring structure that signalizes to us that we're doing something potentially interesting. But now comes an interesting question. Okay, so we are seeing that there is something that somehow has a hole in the middle. Now, is that entangled? Is that an interesting state at all? I mean, we know exactly how many atoms we started with. It's 42 atoms in that experiment. And we can do this tomography but still we don't know if it's an interesting state or not. And that somehow shows, in what state this field is. I mean, you first have to, you thought you were doing something extremely simple, and then you realize we don't even have the metrics to know if the experiment succeeded or not. So first thing, for example, you can calculate the overlap of the state that you've experimentally produced with the closest coherent state. And sure enough, if it has high overlap with the coherent state, then it's probably not interesting. Okay. So actually, the state that we've produced is closer to the W state than any coherent state could be. That was the first thing we found, and was quite a relief. But still, that is not good enough. So how to get further? Actually, we found that we needed to develop our own entanglement criterion in order to move on. But before I tell you more about that. Just to give you more of a feeling for these experiments, actually, of course, the state is not perfect. It's actually very far from being perfect. The fidelity with the W state, oops, what did I do now? The fidelity with the W state is 37%. Yet, in a sense that I'll tell you, it is multiparticle entangled with an entanglement depth of at least 8. But why is it not higher? Well, what is going on here? Actually, we have a competition between two things. Ideally, we would get the state that we contributed on the previous slide. But in the experiment, of course, there is some spontaneous emission left. It's not completely zero. And the more we detect, that is, the more intensity in the probe beam we have, the more spontaneous emission we produce. That is one limit. So we would like to reduce the intensity of a probe beam and measure less. So that would reduce the effective measurement rate. And at some stage, the measurement rate would be so low that actually the state in its coherent dynamics can reach the South Pole, which we wanted to block. And that's the other limit. So we have to make a compromise between these two limits. We can see in our experimental data that it peaks at a certain measurement rate, which corresponds to the best compromise between these two extremes. But how can we actually tell that it has this entanglement and this amount of it? Well, to do that, first of all, how do we actually get that data that I showed to you? Well, it turns out that that was actually another surprise to me. With our primitive quantum measurement that can only ever measure population at the South Pole of the sphere, it turns out that this, combined with our coherent microwaves, is enough to do a full tomography of the surface of this Bloch sphere. Actually, it's because there is a something called the Husimi-Q distribution, which some of you may know, which is a bit like the Wigner distribution, except that it is it doesn't get negative, but in principle it contains full information about the state, and it does so in the following way. Well, you measure the overlap of your density matrix with a given coherent state defined by angles theta and phi, and the integrality of these values for different theta and phi gives you full information about your density matrix. That's the idea. And in the experiment, well, instead of rotating our measurement by theta and phi, we can also rotate the quantum state and then measure population at always the same point. And that is what we do. So in order to take this tomographic data that I've shown before, actually what we've done is always rotate the Bloch sphere with microwave radiation, then do a cavity measurement that gives us just one bit of information, 0 or 1. Then we repeat for the same angles a lot of times, typically over 100 times. That gives us 1 point in the tomography. And so these 7 times 7 points for different experimental parameters that you have here took a full week of measurement. So compared to ion traps and even more compared to superconducting qubits, it's very slow, but it gives us what we want. But now we want to know how good this state is, so let me come back to that question. well, the criterion that we came up with is inspired by the entanglement depth criterion that had been developed before in the context of spin-squeezed states, where you ask a question, out of my n atoms, how many of them do I need to entangle at least in order to produce a state that is compatible with the experimental data that I get? Okay, so you ask a question that way around. So for example, you theoretically take all states that have up to 2-particle entanglement only, and then what we did was compute the best combination of ground state population and W state population that we could possibly get with just single particle entanglement. And that is this blue line here. And then same thing for up to 2 entangled atoms, clusters of 3 entangled atoms, 4 entangled atoms, and so on. And then you see where your experimental data is with respect to these lines. And here our best point is above the line for that corresponds to isn't this? It's not written here. Yes, it is. For 16 entangled particles in that particular experiment. So that means that in order to explain this combination of rho 11 and rho 00, you need to have clusters of at least 16 entangled atoms out of your 42 atoms in total. Okay, so that's the sense in which we have 16 particle entanglement for example, in this particular experiment. Of course, you could say that an inconvenience of this method is that, well, you know that you need these clusters of at least 16 entangled atoms, but you don't say anything about how entangled the atoms are inside each of these clusters, which could potentially be low. Yes. It's a question that I have no elements to go further on, but which again seems to show that there's more work needed here in order to come up, with measurement metrics, entanglement witnesses, and other forms of things that you can measure easily. Otherwise, we cannot make any progress on this multi-particle entanglement. And this scheme here that we came up with to characterize our entanglement. It was developed by Jérôme Estève in our group. It involved mathematics that I would be incapable of doing. You need Lagrange multipliers and whatnots in order to enumerate all these states and get these green curves here. But he did that, and once he had that, this entanglement criterion developed a life on its own, was used by other groups, by Vladan Vuletic, for example, who showed that with a different scheme he could get up to 1,000 entangled atoms. And now there's a real Olympics going on here, and there were 2 articles published last year in the field of quantum memories, where they showed that using a similar entanglement depth concept, they had more than 10 to the 9 entangled ions in a solid state system. That's an impressive number, isn't it? And so you ask yourself, does that make sense? Or if it makes sense, is it a completely useless number? And thinking about it, well, I tend to think that no, indeed, it actually measures what they are really interested in, because in this form of quantum memory that they use, what do? You have a single photon incident that you convert into an atomic excitation that is distributed over all these allegedly 10 to the 9 atoms. Why do you do that? Why these high numbers? Well, they need the high numbers, first of all, in order to get a good optical depth, and otherwise they wouldn't absorb the excitation, which is what they want to do in the quantum memory, of course, and so they need the optical depth, and hence the high number of atoms. They also need the fact that this excitation is now coherently distributed over all these atoms, because otherwise, when you convert back into a photon, it could come out in a mode different from the one that you want, right? And so it turns out that indeed, yes, you need something like a W state here, and you need it to have this high number of particles. So after all, it seems to make sense, right? And this explicitly, these articles explicitly trace back their their entanglement statements to this criterion that I showed you on the previous slide. And so maybe this is one thing that you get out of this form of experiments. It drives your curiosity in the right direction and allows you to sharpen your concepts. But nevertheless, the experiments in themselves should progress. And so in the last part of my talk, I'd like to share with you some of the perspectives that I see and that we are also, for some of them, developing in our lab. So what I've shown you was just one way of using quantum xenodynamics. And as I told you, the xenodynamics in itself can be pushed much further. Jean-Michel Raymond showed that essentially any point on the surface of the n-particle loss sphere can be reached by what he called phase-space tweezers, which is a generalization of this method. And although he showed it for photons, I think that could be applied here. But there's another very clever scheme put forward by Vladan Vuletic and this group, which now goes by the name of entangled state carving. And I take it that the name was proposed by Peter. Is that true, Peter? Vladan told me that. And the idea is this. I mean, as we have seen, what our cavity really distinguishes is Dicke states, right? Now, these Dicke states, I mean, I've only shown you an experiment with just one, the first Dicke state, but then they cover this whole sphere, and actually they form a basis of the symmetric states, the surface of this Bloch sphere. So if you can access an arbitrary combination of Dicke states, then actually you can produce any state, and in particular any entangled state of your n-atom system. Now, how could you go about to create that using a cavity? Well, we have already seen that depending on the detuning, you address one or another of these Dicke states, each of them characterized by a precise number of spin-ups or one states in the system. So if you use a cavity that has a given fixed detuning, and then you shine in a probe laser that has a fixed detuning with respect to that coupled system, then you can address one of these states, and if you see transmission, then you project your system into one particular Dicke state. This one, or this one, or this one, depending on the detuning of your probe beam, okay? And yeah, that sounds nice, but that's a single frequency thing. Of course, you need a very strong coupling cavity already in order to distinguish these states, not to get any overlap between them. Higher the cooperativity, the narrower these individual resonances will get. So I can believe that I can, with high enough cooperativity, I can resolve them. Fair enough, but that only ever gives me a single Dicke state. But now what I can do is put in a probe beam that is in a superposition of several different frequencies. And then if that probe beam is transmitted, then I put my atomic system, I project it into a superposition of these Dicke states, and it gets even more beautiful than that. You can easily control the relative phases of these frequency components, and that will determine the relative phases of these Dicke states in the superposition that you create. Isn't that nice? But now, of course, what about spontaneous emission in that system? Well, and now comes another clever idea. If you use a very weak incident beam that on average contains less than a single photon, so that it actually never contains more than one photon, then that means that if you detect that photon in transmission, there cannot have been spontaneous emission. And so if your detector gives you a click, then you have actually produced the state that is defined by the frequencies and phases of your different frequency components. That sounds good. Of course, there are now the practical limitations to that. Of course, your initial state must have a sizable overlap with the state that you want to produce, otherwise your detector will never click. And then there's some fine print associated with, with your resolving power and spontaneous emission and so on. But nevertheless, it seems realistic to produce fairly highly entangled states of atom numbers up to a few hundreds. using that scheme, and so that is something that would be very interesting to realize in the lab. Requires some progress in the cavity, but as I told you several times by now, this is something that that has been achieved by now. So now the things need to be combined, and then maybe this scheme can be put into practice, which would be very cool. One thing that has already been put into practice and that starts from the same principles, once again, the Dicke states being resolved by the cavity, is something that you all know. It's a production of spin-squeezed states. Actually, spin squeezing is produced once again from the same ingredients, a cavity that has Dicke states as a basis. Actually, it can be done in two ways, but I think my time is almost up, so I won't go into details here. But if you have such a cavity as the ones that have been showing to you, then you're all set for producing spin squeezing, and indeed it has been done. Again, Vladan Vuletic's group showed the way, and the best result by now has been achieved by Mark Kasevich and his co-workers, who have produced up more than 20 dBs of spin squeezing. So they have reduced the noise by more than a factor of 100 below what you could get with unentangled atoms. And now the next step, of course, is to actually use that in a useful measurement. And the simplest case would be an atomic clock. There have been proof of principle experiments where spin squeezing has been shown to work in the clock, except that the clock that has been used for that was really a toy clock, not even as good as your wristwatch. And obviously it gets harder as you go into the metrologically useful regime. But if we take our quantum technologies seriously, then we should do that. And of course it's also interesting because it won't be just a straightforward application of what we already know. I'm absolutely sure that we will encounter new physics as we do so, and that is something that we are on the way to doing in a clock that my group developed in collaboration with the CIRT, which is the French Time and Frequency Standards Lab, who have some of the best clocks in the world. This one is definitely not one of the best clocks in the world, but it has the virtue of being very compact. It uses, once again, an atom chip. It has a measured Allen variance, which has a 1 second stability in the 10⁻⁻13 range, which is the interesting range for next generation compact clocks, for example, the ones that will be put onto next generation GPS satellites. And so we'd like to improve that clock using spin squeezing. And so we are in the process of building an experiment that has the clock uses a clock scheme as before, based on an atom chip, but adds a cavity to it in order to produce the entangled state known as a spin squeeze state, and then use that to reduce detection noise in this particular clock. And one question that comes up here is, we know there are spin interactions in this clock already. Actually, this fairly good value that we have already measured is partly due to something called spin self-rephasing, which is a direct interaction of the spins. Now, if we superpose that mechanism with a state that is no longer a coherent state as before, what will happen? Not so clear whether what that will give. Nobody has done the theory for that. I have a hunch that it will not be a harmonious coexistence, but in any case, it will be an interesting question, and we are getting ready to do it. I mean, there's lots of experimental problems to be solved, but the experiment, I mean, we are now at a point where we can reproduce this curve here, and we can use the cavity, but we can't still do the same both things at once. Another project that we have is using, instead of putting all atoms into a single antinode of our cavity, realizing something like a n-qubit register in the cavity, where we only have a maximum of one atom per lattice site, which is interesting for several reasons. For one thing, it helps us to get rid of excited state collisions, which are a loss factor in our previous experiments. But also it will allow us, because we combine it with a high numerical aperture lens in the same system to detect our atoms individually, one by one, so that the tomography will get much more efficient than in the previous experiment. And also, in principle, we would be able to address the atoms one by one, so that we can access the volume of the Bloch sphere and go beyond symmetric states. That experiment as well is approaching the end of a laborious setup phase that got slowed down by the reconstruction work at Rue Laumont, where we work. But I hope we can soon see the first atom by atom resolved images. So in a way, it's a poor man's quantum gas microscope that we are combining here with this cavity system. Although we are not working on it ourselves, this list wouldn't be complete without mentioning that actually these fiber cavities are a very well-suited system to produce, to realize quantum networks, and that indeed is corresponds to ongoing experiments in Gerd Rempe's group in particular. One last thing that we are doing ourselves is realizing a CQED system with an optical qubit instead of the microwave qubit that we have in rubidium. The interesting thing here is that then we will be able to drive a transition between two qubit states that instead of being separated by a few gigahertz are separated by an optical wavelength, while we use another wavelength to address it with the cavity. And in that way, one of the qubit states will now essentially have infinite detuning from the cavity, whereas in the previous experiments, we used the approximation, but it wasn't really true. And now, so actually the quality, the fidelity of the states that we produce will get much better. And of course, when you use alkaline earth atoms that have these optical metastable states, these are also the elements that are being used in optical clocks, where ultimately it will make most sense to apply spin squeezing to. So that's another good reason to do cavity QED with these elements, and that is actually what I'm using my ERC money for. I had no time to talk about other applications of these fiber cavities, but they are no longer limited to atomic physics experiments. There's a lot going on. Those of you who are interested could come to the more specialized talk that Tracy asked me to give you, I think tomorrow, right? I'll talk a bit more about the cavities themselves and how we use them. For example, in solid state systems, we used them recently to make a single photon source with a carbon nanotube in collaboration with solid state physicists in Paris. There's a lot you can do. There's a lot being done in Innsbruck in particular, and I'm looking forward to discussing that. And in general, discussing with many of you. And so now I'll stop talking, and I hope you have a few questions, although I was a bit long. But before ending, let me acknowledge my fabulous group. This year is the team working on the second generation cavity experiment that I showed, and down here are the guys who realized the experiments, especially the quantum Zeno dynamics. This guy here and these fabulous cavities that we now have. And thank you for your attention.
Thank you very much for this very nice talk. So now we open the time for questions. Are there any?
So you mentioned that you had a certain criterion for K atoms being entangled. Is this equivalent to the quantum Fisher information or not?
No, it's not equivalent to the Fisher information. Although we can also derive the Fisher information from once we've done tomography.
But would you get the same result as what you get here?
Does the Fisher information measure entanglement depth?
Yes, you can also, yeah. There's certain criteria, there's certain bounds. And it sort of sounded similar to what you had, but on the other hand, maybe...
Okay, at the time we looked at the Fisher information, of course, but so why did we decide that we couldn't use simply the Fisher information? Was it... Now I don't remember if it was just that it wasn't experimentally robust enough, or whether we were not aware of its link to entanglement depth. I think it was the latter. Okay, so let's look at that.
So I was wondering if you could talk about the kind of ideal cavity parameters that you want for your spin squeezing experiment, because at the beginning of your talk you motivated this high cooperativity regime, but here you showed a picture of this longer fiber cavity of 1.5
Of course,
millimeters.
I simplified a lot by saying that you want the highest possible cooperativity. That is true for these non-destructive detection schemes. There seems to be an optimum cooperativity when it comes to producing spin squeezed states, which depends on the number of atoms. And that is because it's not enough to avoid spontaneous emission. And actually in spin squeezing you can tolerate some. That's what makes spin squeezing so interesting for practical metrology application. And which differs completely from something like a cat state, where the first spontaneous photon completely destroys the state. On the other hand, when you first put your coherent state into the cavity, then you have to continuously deform it into your spin squeezed state, and that means that your cavity needs to be aware of the full distribution that you initially have. And so it simply boils down to higher the number of atoms, the higher the fluctuations, which are square root of n. And you want all these different Dicker states that contribute to your coherent state to be not too far from resonance of the cavity. Otherwise, the cavity will not influence their distribution and will not drive them towards the squeezed state. So it's like the locking range of a feedback loop. You need this locking range to be large enough, and that means that the line width of the cavity shouldn't be too small. And then things can get technical, like when you read the fine print in Markasevic's article, he actually used a succession of 2 different squeezing schemes in order to first drive its system into the locking range of the squeezing scheme that worked better but had a lower locking range. Yes, so I'm not sure how much I can say about that in full generality. One nice thing would be to have a cavity with adjustable finesse.
Good question. So could you elaborate a bit more when you were talking about the compact clocks on an atom chip, that there were these limitations due to decoherence, due to spins? So what is the microscopic origin of that, and how do you plan to overcome this?
Well, actually, what I was alluding to and what is already going on even without a cavity is that in this particular clock, it's a trapped atom clock. That's what makes it so compact. But that also increases the density compared to what you are used to in atomic clocks, and that is what makes the spins interact.
Okay, that was interaction of spins.
Yes, and then what you have is something that some people call identical spin rotation effect. So the spin statistics, even in thermal ensemble, are influenced by the fact that these are bosons, and so to identical spins colliding don't drive you into the same state as to different spins. And in a spin ensemble, what that leads to is that if you have spins that are not perfectly aligned, so decoherence, then due to the collisions, they start to rotate around their sum. The sum is conserved, of course, but they start to rotate around it because of the statistical effect. And that acts like a spin echo. And this spin echo is beneficial. And for that reason, we have a coherence time of a minute where we expected only 3 or 4 seconds. But how will that coexist with spin squeezing? That's an open question.
Are there any further questions? Okay, so if this is not the case, let's thank the speaker again.
Thank you.
And I recall you that we have some beverages and drinks outside so that you can also use the time to discuss further with the speaker.